Hello everyone, today we'll talk about the solution to the problem maximum number of K-divisible components. This is a problem on a tree where we have to calculate the maximum number of components into which we can split the tree such that the sum of values in every component is divisible by K. When we have problems on trees, then typically our solution will resemble tree dynamic programming, tree DP. We can implement it however we want. We can implement it top-down using essentially a DFS, which is what I'll do in my solution. We can implement it bottom-up, but typically we will be thinking about the tree as a rooted tree. We'll probably not root it explicitly, but we'll imagine it as rooted in some arbitrary vertex. And since we are given here a list of edges, we'll probably have to transform it into something more convenient. So for bottom-up, we'll probably do some sort of topological sorting so that we can start with leaves. And for top-down, we just want to create a graph. So the graph creation is very simple. For every edge, we add appropriate vertices to each other's adjacency lists. Okay, so how do we actually solve this problem? Because when we have 3DP, then we want to calculate something for every subtree of a given node that we're looking at. And that something has to be the answer to the question, of course. And also some other things that we'll later use to calculate the answer to the question for our subtree based on the answers for our children's subtrees. And we also have to calculate those auxiliary things. In this case, those auxiliary things will be the sum of values of all the nodes that are not part of any component. Luckily for us, at this point, we don't have to do much more. That's because if we think about those correct splits that we can create by removing edges, because this is the only operation that we can do, then we see some easy things. For instance, if there is a component that's part of some subtree, then it's entirely contained within that subtree, right? That component is created by removing a single edge from our tree. Maybe there are some other components that were removed first, but still, it's just cut off from some subtree. So for instance, we cannot have a situation where we have two children and they have two small components somewhere deep within their subtrees that we can later connect. That's not true. Every child can cut off components within its own subtree, and the only thing that remains is either nothing, because everything is split into subtrees and into components, and we're happy in that case, or there remains some set of nodes, but that set of nodes includes that child, and some other things may be connected to that child. But it still has to be a single connected component that has the child as one of the nodes. And so what we can do is, if we want to calculate for some vertex u both the count of good components and the sum of remaining values of the remaining component that contains this node u. At first, of course, the sum is just the value of u, and we have no components. For every neighbor, here of course we'll have to remember this back pointer to our parent so that we never loop in our DFS. So for every neighbor of our node u that's not the neighbor we've just come from, we have to recurse into that neighbor. So we get the count of components for that neighbor and the possible sum of values remaining that are not part of any component. And we'll have to connect it then to our component that contains only this vertex u. So we add nv to our v and nc to our c. All those components are still good for our subtree, and we have to add the values to our sum of values. Now it's also possible that after all this, we can actually create a component from what remains here that includes our node and all those rests from all the other subtrees. And in that case, there is nothing remaining and we have one more component. And that's what we return. And note here that this is only there is only the possibility of either us not creating any component and putting this sum of v's, pushing it as a result up the call stack, or we can create a single component by taking all of it together. We cannot create more of those. That's because they would either have been created within a single subtree of one of our children, and we cannot connect two of our children together, because that would include our node, because we have to connect them somehow. They still have to be connected. And so that means that everything else would be disconnected in that case. So either we take everything together as a component that's okay, or everything together as a component that's not okay, and somebody has to deal with that up the call stack. And now we have to just run from any vertex that we want, so for instance from 0, and we return the count of components.